Welcome to this biochemistry presentation on protein quaternary structure. As you might be aware, there are 4 levels of protein structure. There is the primary amino acid sequence, there's secondary structure, which are localized to regions of structure within a polypeptide chain. There's the tertiary structure, which is the overall structure of a polypeptide chain, and then there's quaternary structure, where we have the interaction between multiple polypeptide chains. Today, we're going to talk about the quaternary structure of a protein, in particular a protein complex. So again, the quaternary structure is the arrangement of these polypeptide chains into a non-covalently bonded aggregation. Again, generally these things are non-covalently interacted. There's always an exception, and it's probably more prevalent than we think, but sometimes disulfide bonds can link quaternary structures together. You'll see this in things like immunoglobulins. But generally speaking, non-covalent interactions keep these molecules together, just like they do in tertiary structure, just like they do in secondary structure. So all the same ones: hydrogen bonds, salt bridges, hydrophobic interactions, etc. The classic example of quaternary structure is always hemoglobin. There are 4 subunits within a hemoglobin, so it's a tetramer. There's 2 alpha and 2 beta subunits, and they form together to form the hemoglobin molecule. And that provides important oxygen, and carbon dioxide removal for cellular respiration. There are other things like integral membrane proteins and on the outside of a cell. Quaternary structure is very, very important. Enzymes like things like ribosomes are also, again, immunoglobulins. Those provide important functionality. There's cell receptors. So there's all kinds of applications for the quaternary structure to exist. A couple of other examples, in enzymes, you see the FO-F1 ATPase. That's important for generating ATP across the mitochondrial membrane. And you'll notice in this that there are dimers, or polymers, that do some of the work in the complex. You have an alpha, beta. There's 3 alphas and 3 betas within that. There's important quaternary structure. You also have a gamma and a delta subunits, epsilon subunits, and all of these have formed this complex molecular machinery that allows your cell to produce ATP through a pump. So there's a pump going on that's pumping protons out, and the cell is using that electrochemical gradient to generate ATP, which is a discussion for a different day. But you'll notice that the important part of this is there's a quaternary structure that allows that performs important function within a cell, and that some of these actually do work. Another example are the fusion proteins that you see in viruses. This is the fusion protein for herpes, glycoprotein B. It's a trimer, so there's 3 subunits or 3 polypeptide chains in there. They form this complex. The GB protein has fusion arms that reach up, grab the cell membrane, and cause the cell membranes of a virus and a cell to fuse. This also performs important molecular work, and these are all put together generally with non-covalent interactions. There's also things like the proteasome, the spliceosome. All kinds of these things do machinery, and they're also used as receptors. So these protein complexes are very, very important in a quaternary structure of proteins, which allows us to build up to the next thing, which is next topic of discussion, which is protein-protein interactions. I hope you enjoyed this, and we'll look forward to seeing you in the next video.